Okay, let's continue to finish the proof of theorem 3.4. Before that, let's recall what is the theorem 3.4. Assume we have a sequence Fn in the M of G, meromorphic functions, and Fn converges to F in CGC infinity. Okay, remember that CGC infinity has that metric, the metric D, Z1, Z2 is 2 ops value Z1 minus Z2 over square root of 1 plus ops value of Z1 squared, 1 plus ops value of Z2 squared. Okay, this is distance. This here Z1, Z2 are in C, and the distance between Z and the infinity is just 2 over square root of 1 plus ops value of Z squared. Okay, so this is the distance in the CGC infinity. And for any sequence Fn in Mg, sequence Fn converges to F, then the statement says then either F is meromorphic, F belongs to Mg, M of G, or F is constant infinity, F is constantly infinity. Okay, so this is our statement 1. And statement 2 says if in addition Fn is analytic, you have an analytic sequence, then either F is analytic or F is constantly infinity. Okay, this is the second part. And in the last video, we proved that we already proved one thing. If f of a, the limit function f of a, is not equal to infinity, if f of a is not equal to infinity, then there is an r greater than 0 such that this f is analytic inside this ball centered at A with radius r. So this is what we proved. We proved this. Okay? And let's prove the other one, the other case. So here, if you have a good point, not infinity, then around it, it's going to be good. That's what it means in the first part. Now let's see what happens if it is a bad point. Now, suppose that Fa is infinity. Okay, Fa is infinity. At this moment, we don't claim anything about F. F is just a limit. Okay, F is just a limit. It may not be meromorphic. We don't know if it is meromorphic or not. F equal to constant infinity, that's not a meromorphic function. That is just a continuous function in C infinity, but it's not a meromorphic. Okay. Okay, so assume we have a point A such that f of A is infinity. Then for a function G in CGC infinity, we define the reciprocal of G, 1 over G by 1 over G evaluated at Z is equal to 1 over G of Z. Okay, just a reciprocal, pointwise. And here, if G of Z, remember, denominator cannot be 0. And it cannot be infinite. We don't have 1 over infinity. Only for the regular number, we flip it. And 1 over G of Z is 0 if g of z is infinity. So if you really have g of z equal to infinity, denominator is infinity, the reciprocal of infinity, we understand it as 0. And 1 over g of z is equal to infinity if g of z is 0. If the denominator is 0, we understand it as infinity. So there are 3 parts of the definition. If it's good enough, then it's a reciprocal. If it's bad, 0 is defined to be infinity. Infinity, the reciprocal we define it to be 0. Okay? And then we get that the reciprocal of g also belong to CG C infinity. That's an advantage of C infinity. Okay, so remember that for the distance d has an interesting property. dz1, z2 is equal to the distance of 1 over z1 and 1 over z2. So there's such interesting property, okay? Okay, so how do we use this? So Fn converges to F in CG C infinity. So 1 over Fn converges to 1 over F in CG C infinity because of this equality of the distance. Okay? Fn is a meromorphic function. Meromorphic function has isolated pole. It also has isolated 0. And after you flip it, isolated 0 becomes isolated pole, and isolated pole becomes isolated 0. So it implies 1 over Fn is also meromorphic. Okay? So for meromorphic function in CGC infinity, 1 over Fn is also meromorphic. Pole and zeros are still both isolated. Okay? So this implies, you see, 1 over Fn approaches 1 over F, and remember that 1 over F of A is equal to what? Is equal to 0, right? Because we assume here Fa is infinity. Fa is infinity, 1 over F evaluated at A is 0. So this is not infinity. Then by the first part, 1 over F is non-infinity. It's not infinity. Then there is an R greater than 0 such that 1 over F is analytic in the open disk centered at A with radius R. It is analytic centered at A with radius R, right? And also, we choose this R small enough, 1 over F, 1 over Fn are all analytic in the ball centered at A with radius R for n sufficiently large n, n is greater than or equal to n0 for some integer n0. Okay, because 1 over Fn converges to 1 over F, so in the, for any epsilon inside the n is greater than n0, 1 over Fn is close to 1 over F, then they are both analytic. Okay, they are not infinity, so they are both analytic. And the convergence is uniform. Is uniform on this open disk. So actually, first of all, the convergence is not guaranteed uniform over open disk. But for this open disk, you choose a small subdisk inside it, and you choose a closure, then the convergence becomes uniform over that closed closed disk, and then you choose that open. Okay, so first you choose this bigger R, and then inside it you choose a small r, and small r, the closure is compact, then the convergence becomes uniform convergence. So inside this smaller open disk, the convergence is still uniform convergence. So we just shrink it a little bit. But in this process, you do not see that shrinking process. Okay? Okay, so you have uniform convergence, then by the Hurwitz theorem, then either 1 over f is constantly 0, or 1 over f it has isolated zeros. Okay? In this open disk. But we know that f is analytic, so it cannot be constantly 0. F is not constant infinity. If f is not constant infinity, then you get 1 over f is not constant 0. We always discuss a non-constant infinite situation. If it is constantly infinity, the theorem is already proved, so we don't discuss it. So f is not infinity, constantly infinity, then 1 over f is not constantly 0. 1 over f is not constantly 0, then 1 over f has isolated zeros in this ball BAR. Okay, it has isolated balls in this BAR. So in this part, you see this part, we only see that 1 over f is analytic, but we don't know if 1 over f is constantly 0 or not. So here we just try to make sure that it has isolated 0 there. Okay, and it has isolated 0, then you flip it, it will have isolated poles. Meromorphic. Isolated poles means it's a meromorphic function. It's meromorphic in this neighborhood. So 1 fa is infinity, but inside this neighborhood, a is a unique infinity. So this is a meromorphic, right? Okay, so we proved that good point in the neighborhood is good. Bad point in the neighborhood, that is unique bad point. Then that's a meromorphic. So we finished this one, the first part. We finished the first part. We always say if it's not constantly infinity. Okay, and second part, if the sequence Fn is analytic. So if Fn is analytic, then 1 over Fn has no zeros. Why? In this BAR. How do we get 1 over Fn 0? If Fn is infinity, 1 over infinity is 0. But Fn is analytic. Fn of A is never 0. A is never infinity. So 1 over Fn is never 0. Right? Here it's because Fn of Z is always less than infinity for all Z in this BAR. It's analytic function. Analytic function has no infinity, no poles. Okay, again, by the Hurwitz theorem, either 1 over f is constantly 0 or 1 over f never vanishes, because Fn has no zeros, so inside it f has no zeros. 1 over Fn has no zeros, then 1 over f also has no zeros. They have the same number of zeros and the poles. There's no pole, so they only have zeros. If it's 1 of f is not constantly 0, then it will never vanish. It has no 0. But we already see that fa is infinity. Fa is infinity. Then we get 1 over f has at least 1, 0. 1 over f must have a 0. Here it says 1 over f never vanishes. This situation will not happen. This condition will not happen. Then it implies 1 over f is constantly 0. So 1 over f is constantly 0. Constantly 0 implies f is constantly infinity in this BAR. Okay, so what? You see, if you have fa is infinity, then fn is analytic, then it will be constantly infinity. If fa is not infinity, then f is going to be analytic. Okay, f is analytic at every point, not infinity. Okay, so this implies, together with part 1, we showed that f is either constantly infinity or f is analytic in G. This part gave us constant infinity. The first proof gave us analytic part. All right, let's finish the whole proof. So meromorphic function, the set of meromorphic function is not complete. So this is a proof. So here we want to emphasize this set is not complete. Remember CG C infinity. Remember that H of G is complete in CGC. Okay, so these two types of sets are different, but even though it's not complete, if you union infinity, this is a complete metric space. Okay, so the only missing point, accumulation point, is infinity. Okay, so this is the first the statement, the result from the first part here, and the conclusion of the second part says the H of G, the set of all analytic functions together with infinity, is closed in CG C infinity. So if you consider CGC, it's not, it is complete, but HG is not complete, also not complete in CGC infinity. Remember, whenever you have C infinity, you use that metric D. When you have C, you just use the distance. Okay, so together with the infinity, it becomes closed. Okay. Okay, so these two are just an explanation or the direct translation of the previous theorem, theorem 3.4. Next, we're going to do some similar problem in MG. In HFG, after we show it is complete, we want to classify the normal family, okay, locally bounded. And here, we also want to classify the normal family. But for the MG, the normality depends on another quantity. So for the normality of MG, we introduce the following quantity. Okay, what quantity? We introduce this quantity. 2 times ops value of f prime of z over 1 plus ops value of f of z norm square. Okay, we want to study this quantity. Check that this quantity is very, very close to the distance. Remember that the distance, where is the distance? Distance, this one. You replace z1 by f of z. You replace z1 by f of z. Both by f of z. z1 minus z2 is a delta, so fz1 minus fz2 ops value 2 square root 1 plus f of z1 square 1 plus f of z2 norm square. If z1, z2 are very close, then this one is approximately by 2 of the fz prime and delta z, or dz. Okay, the differential dz. Here, denominator fz1, fz2, they are almost the same. Then you have a 1 plus ops value f of z, ops value squared, and then this twice take square root is 1 plus ops value f of z. Okay, so you see, that's exactly the same stuff. So these two quantities are related, these two. Okay. Now, let's say this quantity, it makes sense when f of z is not equal to infinity. If f of z is infinity, this does not make sense. The above expression does not make sense. Does not make sense, right? Because the denominator becomes infinite. Numerator f prime of z, I don't know if f prime of z is infinite or not. If it's not infinite, it's 0. If it is infinite, you have infinite over infinity. That's an indeterminate form. We don't know. Okay, so in order to cover the case of the pole, we want to study this expression. We can only study the expression for the good point, okay? So what is a good point? Remember, for the pole, for the meromorphic function, we have the Laurent expansion. Laurent expansion says every meromorphic function is a sum of an analytic function with a singular part. With a singular part, okay? In the neighborhood close to A, close to point A, if A is a pole. and the g of z is analytic around A. This part is analytic. M is the order of the pole. M is the order of the pole. Okay, and now let's try to differentiate f. We differentiate f, we'll get a g prime of z. No, it's not plus, it's minus. Minus, you see, it's negative m, am, z minus a, m plus 1, minus m minus 1, am minus 1, z minus a, mth power, minus a over z minus a squared. Okay, so this is the derivative. Okay, and then let's form this expression. We only do this around a pole of order m. Then this expression, 2 ops value f prime of z over 1 plus ops value f of z squared. F of z squared. Let's try to compute. This is f prime. F prime g prime of z minus m am z minus a to power m plus 1 m minus 1 am minus 1 z minus a to power m minus a1 z minus a to power 2. This numerator, denominator. It's 1 plus ops value, just add them. Z, g of z, am, z minus a, m, a1, z minus a, ops value square. Okay, and then what do? We multiply top and bottom by z minus a to power 2m, because here is a z minus a to power m and the squared 2m. Z minus ops value, z minus a to power 2m. Z minus a to power 2m. Okay, both from top and bottom. Okay, and then you distribute it. You distribute this into it, you will get 2. And this is z minus a to power 2m g prime of z minus, here you cancel this, you will get m am here, yeah, I think I this one, check here. This is a am z minus a to power negative m, and when we differentiate, it's a negative m am z minus a to power negative m minus 1. It's right? Power rule, subtract 1. Okay, yeah, it's right. It's right, then let me try to do it. Okay, here it's a z minus a to power m, 2m a1 z minus a to power square z minus a to power 2m. It's a numerator, and denominator it's a z minus a to power 2m. That's the first term, and plus g of z times z minus a mth power plus am plus a1 z minus a to mth power over z minus a and square. Okay, Let me see if I make mistake or not. So far, I think I'm right. And how do we? Then this one, okay. Then this one, okay. Let's try to see the numerator. 2 ops value z minus a to power 2m g prime of z. Here is minus m a m. Here's a z minus a to power 2m minus m minus 1. It's a m minus 1. And the final thing is it's a minus. It's always minus. A1 and z minus a to power 2m minus 2. Ops value. And the denominator, nothing changes. You have to copy it. And square. So it's m minus 1. And then we factor out z minus a to power m minus 1. So it's 2 ops value z minus a to power m minus 1. And then the first term, it becomes z minus a to power m plus 1. M minus 1 plus m plus 1 is 2m. Then g prime of z and m am. The first term has no such term. And minus a1 what? You remove m minus 1, you still have z minus a to power m minus 1. Ops value z minus a to power m and plus this gz z minus a to power m am a1 z minus a to power m minus 1 squared. Okay? And now let's see. If m is equal to 1, so be careful, here is m minus 1. In the textbook, the author has m plus 1. Okay? That's not correct, I believe. Well, we check the proof of computation. Okay, be careful about this number. It's 157. In the textbook, it says m plus 1. It should be m minus 1. Okay, if m is equal to 1, then this term disappears. M is 1, it's a 0. Z minus a to 0's power is up. It's just 1. So when m is equal to 1, this 2 ops value f prime of z over 1 plus ops value f of z squared becomes what? This is 1, so it's 2 z minus a squared g prime of z and minus a1. That's it. That's the numerator. And the denominator. The denominator, what is the denominator? Here, z minus a to power, m is 1, so it's 2 plus g of z times z minus a, m is 1, and plus a, m is 1, square. Right? So when you let z approach a, this limit to 2 ops value f prime of z, 1 plus ops value f of z square. Z approach A, this term disappear. This term disappear. This term disappear. You have 2 ops value of A1 over A1 ops value squared. So you have this. This is how you get this quantity. You must have minus 1, not plus 1. Okay? You must have the minus 1. If m is greater than or equal to 2, bigger pole, a bigger order. If m is greater than or equal to 2, check here the limit z approaching A, 2 ops value f prime of z over 1 plus ops value f of z squared. What it is, inside is going to be equal to this. So inside the ops value is a negative m am. So negative m am ops value. Because z approach A, this term disappear. All other terms disappear. Only m am survives. And outside, it's a z approach A, it's 2 times 0. And in the denominator part, this is 0 plus ops value. Here is 0. And the whole tail is 0. But you leave am there. This term does not disappear. So it's am squared. So the denominator is non-zero. Numerator is 0. So this is 0. Okay, so we do have the statement on page 158. On page 158, you get those two quantities, but you have to understand how do you get those quantities. Okay, so when you have a regular point z, then you just define 2 times ops value f prime of z over 1 plus ops value f of z squared. When you have a pole, you cannot directly define it, but you can use a limit to define it. Okay? So definition. The definition is the following. If f is a meromorphic function, on the region G, then define mu f from G to R by the following thing. Mu f of z is defined to be 2 ops value f prime of z over 1 plus ops value f of z squared, where z is not a pole of f, and mu of f of z a is defined to be the limit z approaching A to f prime of z ops value over 1 plus ops value f of z squared. So when you have a pole, you do the approximation where A is a pole of f. And the argument tells us when the order of the pole is greater than or equal to 2, this is always 0. When the order of 2 is not order of A is not equal to 2, is equal to 1, it is equal to 2 over ops value of A1. All right, so it's always this. And we can see that this mu of f belongs to CGC, not infinity. There's no infinity. Okay? And we can also see that, remember that the argument I put it here. One is the first one, second one. When Z1, Z2 are very close, then the distance fz1, fz2 is approximately this mu of f evaluated at one of that point and times z1 minus z2, the different distance, dz is the difference, okay? So it comes from this differential part of the numerator. Denominator, you just use approximation to move it out, okay? So if this is an observation, so if mu of f is bounded, then f is Lipschitz. What is the Lipschitz function? Lipschitz is a Lipschitz function. Lipschitz function means if fx minus fy is always less than or equal to some constant k times x minus y ops value, then f is a Lipschitz function. Here, if mu f is bounded, then the distance is less than or equal to the bounds times the distance between z1 and z2. Then f is a Lipschitz. Okay? So if f belongs to a function, a family of function, so this is an observation for one function f. If f belongs to a family of functions, and mu of f is uniformly bounded, for all f in this family, then this family is uniformly Lipschitz, is a uniformly Lipschitz set. What is a uniformly Lipschitz set? Here this k depends on function f. F changes, its k may change. But uniformly Lipschitz set means that this k will work for every element from the family. Okay? Lipschitz set of functions. If it is uniformly Lipschitz set of function, you will get a normal family. All right? So that is the purpose for the theorem 3.8, which we will discuss in the next video. It's long. It can never be covered in 10 minutes. So I'm going to leave theorem 3.8 in the next video, and we are going to study the normality of a family in the MG in CGC infinity in terms of this mu f, mu f function. Okay, so I finished this video and we will continue in the next video. Thank you.